turn.
Okay, thank you. Well, it's a pleasure to introduce my friend Alexandre Fernandes from Universidade Federal do Ceará. He's a specialist on Lipschitz geometry of singularities and is well known for proving important results in theory of singularities. Among them, I can list the beautiful classification of complex analytic curves under bi-Lipschitz equivalence, the existence of singularities which are not inermetically conical in collaboration with bi-Birbrair, and with several collaborators, he answered the abstract Metz-Bizarris conjecture for the multiplicity and the Fukui-Kurika-Palnese conjecture for the multiplicity as well. Today he will give a talk entitled on a theorem of Birbrair, a global point of view. Thank you very much, Alexandre, for accepting the invitation. You can start when you are ready.
Thank you very much for this very nice introduction, Edson. Thank you also for the invitation. It's really a pleasure to speak here in this seminar. So it's a great opportunity to talk about a theorem which lives in my heart. This theorem was proved, the first version of this theorem, as I said in the title of the talk, was proved by Birbrair, and he introduced me in research in mathematics using this theorem. And this is part of my history in mathematics, and it's a great pleasure to talk about these theorems in this seminar. So this year, maybe you know, we are celebrating the 6th birthday of Lev, and it's I'm happy for that. Okay, so I will talk about the joint work with Edson Sampaio. We start to think a problem in mathematics, and quickly we arrived in a theorem of Lev, and I will explain how we arrived there. So the problem is, we thought about global classification of semialgebraic surface up to inner bi-Lipschitz homomorphisms. What I mean by semialgebraic surface, they are semialgebraic sets, which are topological manifolds. Okay. And what I mean by inner bi-Lipschitz homomorphisms, we equip such surface with the distance of the geodesic distance. I mean, geodesic distance means you take 2 points on the surface, and you take arcs connecting those points, and you take the infimum of the length of such arcs. Okay, it's also called the geodesic distance, and our surfaces are equipped with this metric, this distance. And once we have metric there, we can talk about Lipschitz mappings and also bi-Lipschitz homomorphism. Let me explain what I mean by bi-Lipschitz. So you have two surfaces, x tilde, and you have points here, x and y. And bi-Lipschitz homomorphism means we have a biunivoc transformation which sends x to x tilde and y to y tilde. So this is a homomorphism, but we are not allowed to stretch those points too much. The following sense: the distance between x tilde and y tilde cannot be bigger than k times the distance between x and y. As you can think, as we don't have energy enough to stretch the surface, okay? And also the inverse mapping has the same property. Then you can deform x to x tilde, but you don't have energy enough to stretch the surface. So if you have any question, you can interrupt me during the talk. Feel free to do that, okay? So then you think about classification of surface up to in a bi-Lipschitz homeomorphism. This is the problem. Okay? And if you think about compact surface without singularities, everybody knows you have a classification up to homeomorphisms and also up to diffeomorphisms. And this classification coincides with the bi-Lipschitz classifications. We have nothing to do. We have the models of such a surface are spheres, and spheres with the handle attached in there. The torus is a sphere when we attach a handle, and the collection of orientable surfaces are spheres and a torus and connect sum of tori. And if you are not orientable, you have a sphere, or you have a sphere with the cross cap attached, which is a projective plane, and you have some of those objects, spheres with some cross cap attached. This is the complete classification. Then you have nothing to do if you are compact and without singularity. Then when you think about something which is not compact, then as far as we know, and we didn't know any reference of such a classification for sets who are not bounded. Okay? We are compact, we are semi-algebraic, we are properly embedded in Rn, but we are not compact. What about the bi-Lipschitz classification of such objects? This is the problem, and quickly we arrived in the paper of Lev, with this very nice paper of Lev. When we are not compact, of course, you can think about singularity at infinity. And this paper was published in 1999, is about a local bi-Lipschitz classification of two-dimensional semialgebraic sets. This is a local classification. Lev classified singularities of surface equipped with the inner distance. So let me read this abstract here. We present a combinatorial invariant for the problem of local bi-Lipschitz classification of two-dimensional semialgebraic or subanalytic sets. We call it Holder complex. The invariant is complete in the following sense. Two germs of two-dimensional closed semialgebraic sets are bi-Lipschitz equivalent with respect to the inner distance if and only if the corresponding Holder complex are combinatorially equivalent. So this is a seminal paper in Lipschitz geometry. As far as I know, is a first paper of talking about classification, and this is the reference, the complete reference of the paper. And the theorem, what we are using here is the following. Suppose you have a germ of two-dimensional semialgebraic normal singularity. Normal means the singularity, the link of the singularities are connected, okay? This is what I mean by normal. When you take the set and you look the set close to the singular points and intersect with the a small sphere, this intersection is connected. So suppose all singularities are isolated and normal. Then there exists a unique rational number greater than or equal to 1, such that X is bi-Lipschitz homeomorphic to the beta Horn. Beta Horn is this set described here. Okay, if beta is equal to 1, this is just a code. But if it's not 1, the picture is that, and beta is greater than 1. And any two germs like that are bi-Lipschitz. Any two germs like that are bi-Lipschitz inner homeomorphic if and only if they have the same exponent. Here we call this exponent or Horn exponent. Okay. This is the Theorem of Lev, was published in 1990, but also you can find some version, some preprint version of this paper in 1996. So this is the model of a singularity from the inner bi-Lipschitz point of view, the two-dimensional singularities. And associated to this model, you have one rational number which describes completely the inner Lipschitz geometry, and this number can be computed in this way. So we compute this number, we intersect your singularity with, let me take another color. We intersect your singularity with a small sphere. And this way appears here, this intersection. This intersection, it's what we call link, is in white on the surface. This link here, you compute the length of this link. This is one-dimensional set. Then you compute the one-dimensional Haldorf measure of this set. And you look the asymptotic behavior of this function. Okay. Then the exponent of vanish of this function is this number beta, which is called beta Horn, Horn exponent of the set. This gives all about the Lipschitz geometry of the singularity. It's a complete invariant. This is what the Theorem of Lev said. And the other remark is we can see when this number is equal to 1. Beta equal to 1 is when you have the model as a cone, okay, which is bi-Lipschitz homeomorphic to a plane. The cone is just the graph of the distance to the origin. Take the function, which is the distance to the singular point, and the cone is just the graph of this function, which is Lipschitz. Then the cone is a bi-Lipschitz model, bi-Lipschitz equivalent to the plane from the Lipschitz point of view. They are the same. So beta equals to 1 is the non-singular model from the Lipschitz point of view. Okay, so then you can realize that the point is non-singular from the inner Lipschitz point of view by just with naked eyes, because you look the tangent cone. The tangent cone is the collection of the vectors which are velocities of curves starting the singular point in the surface. In this picture here, the tangent cone is a half line. Then in this case, the dimension is equal to 1, and the dimension of the tangent cone in all the points around the singularity is equal to 2. Then in this picture, the tangent cone of the singularity drops dimension. Okay, the dimension is equal to 1, but in a regular point, the dimension is equal to 2. Then, if this point, in other words, this point is regular from the point of view, I mean, the surface is bi-Lipschitz equivalent to a plane, locally bi-Lipschitz equivalent to the plane, if and only if the tangent cone has dimension 2. It's another way to see that we have singularity from the Lipschitz point of view. Just 2 remarks. And it's important to mention that Lev Birbrair proved much more than that. He also considered singularities, germs of two-dimensional semialgebraic set with non-isolated singularity, and he presents a complete classification of that in terms of combinatorial invariant. So, any question? Any question? No?
No questions.
No question, né? Ok, então. Oh, sorry. Let me come back to the presentation. So, let me define what I mean by surface with isolated singularity. Surface for me are semi-algebraic surface. Also, we can think about subanalytic or definable in a minimal polynomially bounded structure. But for me here is just a two-dimensional semi-algebraic set in Rn, which is closed. I mean, it's properly embedded. And I suppose they are isolated singularities. They have isolated singularity, and all singularities are normal in the sense that the link of the singularities are connected. And we keep such surface with the inner distance. Okay? Then, from now on, surface with isolated singularity are objects like that. Two-dimensional semi-algebraic sets with isolated normal singularity keep with the inner distance. And our goal is to classify such objects up to inner bi-Lipschitz homomorphisms. And you do this following the paper of Lev. So what we need to present a complete invariant. Of course, we need a symbol which says if the surface is orientable or not. Okay. All the surfaces are topological manifolds. Then we can talk about orientability there. And we have a symbol O, which is +1 if the surface is orientable, and -1 otherwise. Okay. We need another number as the genus of the surface. Genus is the following. You take a compactification of such a surface. Okay. The surface, you can realize the surface from the topological point of view. Take a topological manifold, compact, and we remove a finite number of points. Then the genus of this our surface is the genus of the compact one. Okay? And the genus is, if the surface is orientable, is the number of handles attached to the sphere to have the topological model of the surface. And if the surface is not orientable, the number of cross-cap attached to the sphere to have the topological model of the surface. Then we need a symbol which says about orientability or not, and the genus And for each singular point, we need the Birbrair number, which is the Horn exponent. But we can just the Horn exponent of the points which are essential from the Lipschitz point of view. If you have a singular point of the surface which is not singular from the Lipschitz point of view, you don't care about that. We can think about that point as a smooth point. Then you get all this point where the bit exponent is greater than 1, which is equivalent to take all the points, the singular points where the tangent cone is dimension 1, for instance. And for the ends of the surface, which are the ends, we intersect our surface with a big sphere, and remove this intersection of the big ball. When we remove that, we have a finite number of connected components, and this number doesn't depend on the radius of the sphere. If the radius is great enough, then these connected components are called the ends of the surface. For each end, we consider this number here. This number is the intersection of the end with a big sphere, and you compute the length of this intersection, which is a one-dimensional set, and you compute this length, and you look the asymptotical behavior of this function when the radius go to infinity. And you put all of those numbers together. Okay, the first one is the symbol which is about orientability or not. The second one is the genus, and you have a ordered set with all non-trivial Horn exponents, and you order it in this way. And the last one, we take all the exponents associated to the ends, and you order it in this way. This collection of numbers we call Lipschitz code of S, or inner Lipschitz code of S. So the theorem which we proved with Sampaio is the following: two semialgebraic surfaces with normal isolated singularities S and S tilde are inner bi-Lipschitz homomorphic if and only if they have the same inner Lipschitz code. This is the theorem. This is a complete invariant from the Lipschitz point of view, the inner bi-Lipschitz point of view. Okay, the invariant in following the idea of Birbrair. So let's see some examples. Take the cylinder here, which is not compact. Okay, we don't have singularity here. Then this is why. This is why here we have empty set. It means no singularity. This means it's orientable, and we put 1 here, and genus 0. Genus is orientable, genus 0, no singularity, and this couple of numbers here is associated to the ends. When it intersects your set with a big sphere, we have two connected components, one here and another one here. And how you compute the exponent of this component? We intersect with the sphere of radius r. When r is great enough, it means the zeta coordinate is more or less r. Then the intersection is more or less the intersection of the cylinder with the plane with higher r, then which is a circle, and this circle has a constant radius 1 constant. Then this function, we measure the length of the circle is constant. It's 2 pi. Or in other words, it's 2 pi times r power 0. And the 0 here, you put here. Okay? And you have the same for the other end. The other end, the growth of this function is more or less r power 0. Then this number here is 0. Is it clear? Any question? Question? No question? Okay. Then another example. The hyperboloid of one sheet. One sheet, we have just one connected component. And as you see, the set is homeomorphic to the cylinder. It's also diffeomorphic to the cylinder. But let's compute the Lipschitz code of that. As in the cylinder case, this set is orientable. You have also genus 0, no singularities, no sing. But for the ends, we have two ends. One end is here, and the other one is upstairs. And the exponent associated to this end is equal to 1. Okay? Means the intersection of a sphere of radius r is a disk with the radius is a circle if the radius is more or less r. The asymptotical behavior of this radius is r. Then r means r power 1, and this one here goes to, and you have the same to the other end. You can see that this number is equal to 1. Look in the tangent cone at infinity with this, the asymptotic cone of this guy. As in the local case, this exponent is equal to 1 if and only if your surface spread in all directions when r goes to infinity. Then this is the case. You have a two-dimensional set of directions, or one-dimensional set of directions. You take a cone of that, which is a two-dimensional set. This is why the tangent cone at infinity does not drop dimension. Then the exponent is equal to 1. So the Lipschitz code of the hyperboloid of one sheet is not the same with the Lipschitz code of the cylinder. The cylinder is equal to 0, 0. The exponents of the ends are 0, 0, and the hyperboloid is equal to 1, 1. More examples. Take a plane here. The green figure is plane, and the paraboloid is gray. Okay? So the Lipschitz code of the plane, 1 because it is orientable, 0 is the genus, no singularity, one end. But the one end, the exponent is equal to 1 because the tangent cone at infinity of the plane is two-dimensional. The exponent is 1. But for the paraboloid, you also have orientable, genus 0, no singularities, but the exponent is equal to 1/2. The tangent cone at infinity is just this half line here. And when you take the intersection of a sphere of radius r, the zeta coordinate is the size of the zeta coordinate is more or less r. Yeah. Then the radius of this intersection of this paraboloid with the sphere is more or less a circle, and the radius of the circle is given by that. The radius is r power 1.5, and the length of this circle is more or less that, or 2 pi times that. Then this is the asymptotic of this function, the length of this intersection. Then this 1/2 goes to here. Compose this Lipschitz invariant here. Then the plane and the paraboloid are homeomorphic, are also diffeomorphic, but they are not inner bi-Lipschitz homeomorphic. So we have more examples. Okay, the case of affine complex algebraic curves, okay, with normal singularities. I mean, all the singularities are branes. Okay, we don't have more than one irreducible component in the singular points. In this case, the singularities of the curve say nothing about the Lipschitz geometry, because the tangent cone of a curve where the singular points is two-dimensional. Then you don't have essential Lipschitz points in complex curves. Then the inner bi-Lipschitz geometry of complex curve is nothing else than topology. The Lipschitz code is given by this. They are also orientable. The genus. We have no singularities from the Lipschitz point of view, and you compute thus the number of ends. Okay? The number of ends. In particular, two such curves are bi-Lipschitz homeomorphic if and only if they are homeomorphic. One more example. Okay, the global horn. The global horn is the horn, as in the first picture of this talk, but you look this horn from the global point of view. We have orientable, genus 0, and one singular point. And the exponent of this singular point is beta. Okay? This is how we define the exponent of the singular point. We use the Theorem of Birbrair to define this number. And this is given by definition of the set. And you have just one end, and the tangent cone at infinity is two-dimensional. Then the exponent of the end is equal to 1. This is the Lipschitz code of the global beta horn. Okay. Any question? No question?
No questions.
So I'm gonna follow. Okay, this position. Okay, then let me try to give you the sketch of the proof. This proof is also is the same proof of Lev-Birbrair from the local case. Okay, the same. We follow the same proof. As I said in the beginning of the talk, this paper of Lev-Birbrair is quite important to this global classification. Okay, a tube is a piece of a piece a beta horn, but you remove the finite part of this beta horn. You look at infinity, but you change the exponent. The exponents of beta horn are greater than 1, and you take exponent smaller than or equal to 1. Then the picture are like that, as a paraboloid, and you remove the finite part of the paraboloid. You look just infinite. Okay, this is the standard tube here, and any set which is outside a compact is in a bi-Lipschitz homomorph to this standard tube is what we call a tube at infinity. This is a tube, and remark, two tubes at infinity are bi-Lipschitz homomorphic if and only if they have the same tube exponents. Tube exponent is this number here. Okay, this exponent in the standard tube. This is clear. Then we have a reduction in our theorem. In order to prove our theorem that the inner Lipschitz code is a complete bi-Lipschitz invariant, it's enough to prove that the ends of semialgebraic surface are nothing else than tubes at infinity, as Lev proved in the local case. For germs are nothing else than horns. And here we prove that the ends are nothing else than tubes. Let me say why. If you have a semialgebraic surface, of course not compact, you have a finite part of the surface. What I mean by finite part, let me put here an example. We have two singularities. So let me draw this. Two singularities, one singularity of the surface, and you go have two singularities, another singularity, and you have three ends. You have one end, have another end, you have another end. Oh, four ends, sorry. And you have genus of the surface. What I mean by finite part of the surface, finite part is for each singular point, we take a small sphere centered in this point, and we remove what is inside of the sphere. Okay. Remove that. And you take a sphere with great enough radius, intersect with your set, and you remove what is outside of the sphere. Then you remove that. Sorry. Remove that. Then this is a smooth surface with boundary. And the number of boundary components, is equal to the number of boundary components is equal to the number of singular points plus the number of ends. Okay, then in your Lipschitz code, you can cat the number of singular points and the number of ends. So you have this number of boundary components of the finite parts of the surface. And you will also have the genus of this surface with boundary. The genus is equal to the genus what we cat in the Lipschitz code. Is in the Lipschitz code. Okay, then the topology of these finite parts of your surface is encoded in our Lipschitz invariant. Then if you have two surfaces with the same Lipschitz code, then their finite parts are the same from the Lipschitz point of view, because this is enough to classify surface with boundary up to diffeomorphism. But if you are compact, diffeomorphism give you bi-Lipschitz map from the inner point of view. Then how can you recover your Lipschitz geometry of your surface? Just put here some horns. This is component associated to singularities. What we put here? A horn. What is the exponent of the horn? The exponent here is encoded in the Lipschitz code. The exponent here is encoded in the Lipschitz code. And what you put here? And what's the exponent of this tube, this end, is encoded in the Lipschitz code. We put here and we put here, and you put here and, using this Lipschitz code. Then you recover your surface. In other words, if two surfaces, if you prove that your surface, the ends of your surface are tube, you can classify your surface using the Lipschitz code. This is what you have to do. Okay. Any question? No question. So then let's go. So then it's enough to prove that the Lipschitz, the ends of the surface are tubes, are bi-Lipschitz equivalent to standard tubes. So let me define what I mean by standard strip. Standard strip is equivalent to the whole triangle when you look at infinity. So the picture is that, because this exponent here is smaller than 1. This is the picture of a standard strip. It's a plane region, a region in the plane. So a semialgebraic subset of Rn is said an n strip at infinity if it is bi-Lipschitz homeomorph to a standard strip. The model is like that. Something which is bi-Lipschitz homeomorph to a standard strip. Of course, when you remove a compact, because we are looking just the neighborhood of the infinity. Okay. Then the lemma one says the following: if you have two strips, if you spawn it at 1 and at 2, the picture is that you have one strip one strip, and we'll have another one. Sorry, another one strip. Such that the intersection of those strips is a common boundary arc. Okay, I have one strip, x1, I have another one, x2, and you suppose the intersection is a common boundary arc. Then, when you glue to the strip, the union of them is also a strip, and the exponent of the strip is the maximum of eta 1 and eta 2. You prove this in this way. You have one piece is bi-Lipschitz homomorph to a strip. Then you have a homomorphism to this x1 to this strip here. And you have x2 as bi-Lipschitz homomorph to another strip. And you put the other strip downstairs. You put we follow the proof of left. It's the same proof. Then here we are a graph of x equal to x eta 1. Here the graph of x equal to minus x 2. And in order to prove the union is a better strip, you have to prove this guy here is bi-Lipschitz equivalent to a standard better strip. Then you change coordinates here to this set. You take the sum. X plus, okay? I have a bi-Lipschitz homomorph from here to here. And now you see the set here, you can write in this way. Suppose eta 1 is greater than eta 2. And you can write this graph here in this way. Y x1 x eta 1 times 1 plus eta 2 minus eta 1. Then you can use a bi-Lipschitz map to get rid of this part here, this unit here. Then your set is bi-Lipschitz homomorphic to this strip. So this is the way to glue two strips. And the other lemma, if you have two strips, such that the intersection of those two strips are two boundary arcs. I mean, let me come back to draw the picture here. Now is we have one strip here. We have another one here, and the intersection are two common boundary arcs. Then, in this case, we prove the union is a tube. You follow more or less as before, and you prove the union is bi-Lipschitz homomorph to the tube, the standard tube. So then you finish the proof by using Theorem of Gurgel-Fernandes that we have for any semialgebraic set, you can have a stratification of the set by L regular cells. In the case of two-dimensional such as cells, they are strips. You can prove the cells are strips, and you take in the closure of the cells, each end of your set, you can write this end as a union of strips. And using the topological restriction of the end, which is homomorphic to a cylinder, this union gives you a tube, because you glue together and you finish when you have two strips with the intersection are exactly two boundary arcs. And you use the lemma to realize that, in fact, you arrive in a tube. This is the proof. So this result is published with Edson Sampaio, my friend from my department, and accepted for publication in Análise de PISA. And the reference used here was the paper of Lev, the seminal paper of Lev. Okay, and before to finish, let me do just an advertisement. As I said before, this year we are celebrating the 6th birthday of Lev, and we have a math meet. There will be this math meeting to celebrate his 6th birthday in Bedlevo in this July. Okay, all of you are invited to see more about the ideas of Lev in bi-Lipschitz geometry. This is not one idea. This is one of the ideas of Lev. Then I explained today, and there you have much more. So, obrigado pela atenção. Thank you for your attention.